Hello, my name is David Burns. This is my heat transfer semester project. For this project, I wanted to analyze a heat sink in a CPU. Heat sinks have common places in computers. They're used to transfer heat away from the processors to ensure functionality. The effectiveness of a heat sink is a ratio of the heat transferred away utilizing a heat sink compared to the heat transferred away without the heat sink. So for many heat sinks, there's a lot of common shapes and sizes, and there's readily available solutions for these common shapes and sizes. The one I had in mind had a unique design, and so in order to analyze it, I decided to run an experiment to collect data and also to perform a finite element analysis. This is the particular heatsink that I wanted to analyze. I received this heatsink from one of my friends earlier in the semester, and my first steps in analyzing this was to establish boundary conditions. In order to obtain the convection coefficient, I used a lump capacitance method. I calculated a value of 18.38 watts per meter squared Kelvin for the heatsink. And plugging this back in, I got a Biot number of 3 thousandths, which signified that this was an appropriate approximation. In order to get a free stream temperature, I recorded the room temperature atmosphere, and that was 23.22 degrees Celsius. I also picked a base value for the fin, and that I established at 37.78 degrees Celsius. I wanted to experimentally analyze the heat sink by calculating the amount of energy generated required to keep this fin at steady state under the convection conditions. I did this by using an Arduino to set a constant temperature boundary at the base. I then went through and insulated the backing of the heat sink so that essentially all the heat generated would travel through the sink rather than out the back of it. With this being done, I turned on the fan and the Arduino and let it reach steady state. Once the heatsink reached steady state, I began to record the energy generated. I ended up finding that the heat rate was 6.824 watts during this experiment. I next performed a finite element analysis utilizing the ANSYS package here on campus. I ran a steady state thermal analysis within ANSYS, and I made a few simplifications to the geometry. The first was on the photo on the right, you can see that there is a support connecting the heatsink to the screws which fasten it to the CPU board. I ended up replacing these supports with 2 extra fins. I then used the cyclic geometry in order to reduce the computational effort of the analysis. The figure on the left shows the steady state thermal gradient throughout one of the fins. And for this analysis, I ended up with 105.98 watts going through the fin at steady state. In order to calculate the effectiveness, I needed the heat rate without the fin array. In order to do this, I used a simple convection equation and ended up with a heat rate of 0.3196 watts. Utilizing this number, I divided both the experimental and the finite element analysis heat rate by that value in order to obtain the effectiveness. For the experimental analysis, I ended up with an effectiveness of 21.354, and for the finite element analysis, I ended up with an effectiveness of 331.6. In conclusion, the effectiveness for both cases was very high. The effectiveness is usually around 3 to 5, and for the experimental I ended up with 21.4, and the finite element analysis I ended up with 331.6. The reason being this is that in the experimental there was not a sufficient amount of insulation on the back, so quite a bit of heat may have dissipated through the back instead of through the fin where I'd expected most of it to go. So some modifications would need to be made for future references in order to account for that and the heat rate loss out the back. For the finite element analysis, some common causes are probably boundary conditions. I would need to take a look at that and revise those. This has been an overview of my project. Thank you so much for watching, and I hope you've enjoyed it.